Why did a game become the ultimate laboratory? Early computer scientists used chess to test cognitive code. The 64-square board presented an unspoiled, finite universe. It had clear rules, yet it harbored infinite strategic complexity. Could a machine mimic human intuition? This question guided early computer science. DARPA funded this intellectual quest. Chess served as the perfect benchmark. It tested heuristic search techniques. Scientists measured progress with checkmates. The game allowed for direct comparison. The human mind was compared to silicon circuits. This board game shaped modern computing. It unified ideas of isolated programming. The quest was never about winning the game. Could an algorithm truly think? 1962. The United States Advanced Research Projects Agency, DARPA, took a bold step. It established the Office of Information Processing Techniques. J.C.R. Licklider became its first director. He envisioned an integrated model of human-computer symbiosis. The agency wanted powerful and interactive command networks. They needed advanced computational theory. Large amounts of financial support were provided to the best universities. This was an open-ended scientific exploration. In 1963, DARPA provided foundation funding to MIT. Project MAC was born. The acronym stood for Machine-Assisted Cognition. It also stood for Multiple Access Computing. It pioneered early time-sharing systems. Multiple researchers shared a single mainframe. This created an unprecedented collaborative ecosystem. Software developers interacted directly with machines. Before this, programmers used cumbersome punched cards. MIT labs were overflowing with intense creative energy. Hackers worked day and night. They pushed the limits of the hardware. Researchers needed a complex problem. They needed to test their new time-sharing systems. They chose the old game of chess. Could a shared computer compute strategies simultaneously? Could a machine truly mimic human strategic reasoning? In 1963, pioneer John McCarthy delved deep into this challenge. He worked at Stanford and MIT. McCarthy saw chess as a vital microworld, a simplified model of reality. He believed that playing the game revealed how minds organize their choices. He designed programming languages to handle complex data structures. By 1964, the theory had been translated into code. A brilliant student named Alan Kotok emerged. He had received mentorship from McCarthy while working at MIT. Kotok wrote a pioneering chess program. It used a massive IBM 7090 mainframe. The machine filled entire rooms. It had very little memory by modern standards. Yet the Kotok-McCarthy program pushed its limits. It systematically analyzed board positions. It assessed material balance and position safety. This program was a critical turning point. It proved that abstract artificial intelligence theories could run on physical hardware. It was no longer just mathematical equations. It was an active decision-making system. How did the machine perceive the board? It saw numbers, weights, and vectors. It calculated paths through an ever-expanding labyrinth of possibilities. Programmers spent months refining these evaluation values. What happens when brute force coding hits a mathematical wall? In 1964, researchers faced an exponential explosion. Every chess move generated dozens of responses. Computer memory was rapidly running out. They improved the classic minimax algorithm. They integrated alpha-beta pruning techniques. What did this pruning do? It allowed the machine to ignore irrelevant paths. If a move was clearly bad, the computer stopped analyzing it. This mathematical breakthrough made deep search possible. In 1965, academic centers began sharing data. Stanford, MIT, and global laboratories compared their grades. The first software competitions were held. Scientists tested different evaluation functions. One laboratory favored material safety. Another prioritized component activity. This academic competition accelerated algorithmic development. The secret lay in efficient search logic. Software needed to think not just faster, but smarter. These experiments developed early computer science theory. They transformed abstract algorithms into standardized coding practices. Data exchange transcended institutional boundaries. The groundbreaking event occurred in 1966. A brilliant computer hacker named Richard Greenblatt from MIT changed history. He worked at the Artificial Intelligence Laboratory, funded by DARPA. Greenblatt noticed that existing chess programs were playing very poorly. They lacked deep chess knowledge. They relied too much on crude calculations. He decided to write an entirely new program. He named it MAC-6. He used a Digital Equipment Corporation PDP-6 computer. The software was written entirely in Midas assembly language. This choice allowed for direct, high-speed control over the hardware. MAC-6 was quite different from its predecessors. It didn't just rely on brute force searching. It used advanced heuristic evaluation functions. Greenblatt integrated specific chess principles into the code. It recognized vulnerable king positions. It evaluated piece development and central control. The software analyzed positions with unprecedented precision. It efficiently calculated deep tactical variations. Greenblatt also added a significant library of opening moves. The machine instantly recognized classic opening variations. This feature saved valuable calculation time during games. The project reached a significant milestone later that year. In late 1966, MAC-6 entered the human arena. It officially competed in the Massachusetts Amateur Championship. No computer program had ever played in a human tournament before. The tournament hall fell completely silent. Traditional chess players looked at the machine with deep skepticism. Many human players felt openly insulted. They believed chess belonged solely to human intellect. The computer faced immense psychological pressure from the spectators. It remained completely unaffected. It calculated its options relentlessly. The machine lost its initial tournament games. However, it demonstrated remarkable tactical awareness. It did not make silly, random mistakes. It pushed experienced human opponents to their absolute limits. The experiment proved that software could handle strict tournament conditions. This historic milestone shocked the global chess community. The following year brought even greater scientific validation. In 1967, the software achieved a monumental milestone. MAC-6 earned an official performance rating. The United States Chess Federation evaluated its tournament games. The organization officially granted the program a rating of 1243 ELO. This was an astonishing achievement. It meant the computer was no longer a complete novice. It possessed the skills of a competent amateur human. It soon won its first tournament game against a human player. That specific match became legendary in computer science history. People realized that machine intelligence was becoming a reality. It was no longer just wild science fiction. The DARPA-funded infrastructure had delivered a concrete, measurable result. Silicon had successfully entered the human intellectual arena. Could human players maintain their traditional competitive edge? The immense gap between man and machine was closing fast. The computational foundation was firmly established. 5 years of intensive research achieved its ultimate goal. Chess served its purpose perfectly. It acted as the ultimate crucible of early computer science. This work brought together scattered programming ideas. Algorithms developed with DARPA funding formed the basis. The minimax and alpha-beta pruning algorithms still form the basis of modern software systems. They paved the way for advanced neural networks. They directly led to groundbreaking developments in deep learning. The path runs directly from the Kotok-McCarthy program, flows through the tournament success of MAC-6, and culminates in modern systems like Deep Blue and AlphaZero. Today, machines don't just play amateur chess. They effortlessly beat world grandmasters. They solve incredibly complex scientific problems. They started on mainframes with a few lines of code. They grew with Cold War military grants. The first pioneers proved a vital concept, that human thought processes could be modeled. They proved that logic could be automated. They redefined our relationship with technology. We no longer see computers as simple calculators. The ancient game of chess provided the initial spark. The brilliant minds of the first hackers ignited the flame. The digital future was born on a simple chessboard. What hidden boundaries will artificial intelligence overcome next?